Thank you. Thank you for the invitation. And I see. So, okay, so I'd like to speak about, in fact, I forgot an important word in the title. It's more about the discrete harmonic functions. So on ZD, say, we start with the case of ZD. And first, so I would like to discuss positivity and convexity. So let me recall first a theorem in RD. So if U is harmonic, then one can consider the L2 growth function. So Q of R is defined by the average of over the sphere of radius R of U squared. Then to my knowledge, it was first observed by Agmon in 1965 that this function, in fact, is log convex as a function of log R. So in other words, one has a three-circle theorem for this function. Q of 2R is smaller than the square root of Q of R times Q of 4R. And the question is how one can discretize such a theorem, such an inequality. So the one of the key points is the following observation. So let me say that all this work which I'm going to present is a joint with Gabor Lippner from Northeastern. And the key observation to observe is, in fact, that much more stronger property of the Q function is true, that Q is an absolutely monotonic function. Meaning that Q and all its derivatives are non-negative. And an easy way to prove it in Rn is just to observe that this is true for just to check that this is true for the real part and say a function of say in R2. So the same proof works in any R, but true for, say, R for some standard basis of harmonic functions. For example, R to power n times cosine n theta, one can check directly, and then observing that Q behaves nicely with respect to some of such functions. It's a linear combination, so they are orthogonal with respect to each other. So one can see that it is true also for sums. So you get it for harmonic functions. And it turns out that if we want to discretize Agmon theorem, it is much more easy to discretize the absolute monotonicity property than directly the inequality, the three-circle theorem inequality. Yes, so now we can discretize. But again, here we do some, we make our life easier by considering the random walk. So I'm now on ZD, and U is a harmonic function, meaning that its values on the vertices are the average of any value on the neighbor is the value at the vertex, and xn is a random walk from starting from 0. Then you consider the Q function, the discrete Q function. Now, Q of n is defined as the expectation of U squared at time n. And the theorem is that Q is absolutely monotonic. So in the discrete case, it means that all the derivatives of Q are non-negative, but the derivative in the discrete sense, so Qk of n, is defined by Qk minus 1 at n plus 1 minus Qk minus 1 at n. So before I show you the proof, let me do some show some simple application of this statement. Okay, so example is we have, using the theorem, we have an immediate proof of Liouville theorem. So suppose U is bounded by a polynomial. U is harmonic and bounded by a polynomial. Then also it's I want to show that U is a polynomial. So U is we consider its Q function. So Q of n is also bounded by a polynomial. On the other hand, if we look on the Taylor expansion of Q, so Q of n, so the discrete Taylor expansion, we can write it as the sum of Q, the derivative of Q at 0 times n choose k, where k runs from 0 to infinity or to n. And what we know by the theorem that all these discrete derivatives are non-negative. So on the one hand, it should be bounded by a polynomial. On the other hand, all derivatives are non-negative. So it means that from some point on, these derivatives are 0. So Q is a polynomial. OK, so sorry. So we get that Q is a polynomial. And now it is not difficult to check that, in fact, Q of n can be just written in the case of a harmonic function at the sum of all. Sorry, the k derivative of Q is just the sum of all derivatives of k order of U squared at 0. So where Si are just from the set of, say, 4 generators of symmetric generators, or 4n generators of ZD, 4D. And then So we get that all derivatives of kth order of u are 0. And this means that u is a polynomial. So u is a polynomial. So let me say now, tell you the proof of the theorem. In fact, it is an very easy theorem. Its proof is maybe the proof is very simple. But it contains some maybe another interesting fact. So we just okay, we start from the heat equation. So Pnx is the probability to get to point x in n plus 1 steps. So Pn plus 1x minus Pnx is just Laplace of x p. And then we consider, since we have the heat equation, we know that the q of n, q prime of n, is equal to the expectation of Laplace of u squared at point xn. This just follow from the heat equation integration by parts. And after I iterate this, I get qk of n is the expectation of Laplace to power k u squared at point xn. So so what I should show you, so it turns out that in fact, so the claim, the key point in fact, is that Laplace k of u squared is non-negative. And this is an interesting fact, very easy fact, which somehow we could, surprisingly, we cannot find it in the we could not find it in the literature, but it is. So the point is that if you take the k for k equals 1, Laplace of u squared, not only that it is positive, this is positive on any manifold, but it is in fact a sum of squares of harmonic functions in case of Rn. Or Zn, or in fact any abelian group. And just to see it, why, I mean, in R2, for example, just you have ux squared plus uy squared, and the derivative of u is also harmonic. So you have a sum of squares of harmonic functions, so you can iterate. So each power of Laplace applied to u squared is non-negative. Okay, so this gives you the proof of the theorem. And now I would like to relate it to our original goal. Our original goal was to say something about convexity. So maybe here. So as a corollary, we get logarithmic convexity of the Q function, but it's a little different from the case in Rn. So the theorem is like this. So we know so we have Q of so I'll formulate it in one way, but there are a remark about several variants of it. So Q of 2n is bounded by 2 times square root of Qn times Q of 4n. And then we have an additional term, e to power minus square root of n times Q of 4n. Okay, so let me remark about this formulation of the three-circle theorem, the discrete three-circle theorem. So first, I would like to say something about this term, which we call the error term. So I would like to say that we can. It's not true. A theorem. I mean, one cannot have a theorem without the error term, and just by because in the discrete setting you can always construct. So cannot avoid error. In the discrete setting, you can always construct a function, a harmonic function on ZD, which is 0 on a ball of radius r, and is not 0 on a ball of radius 2r. So it's not 0, but okay. So such an extended to a harmonic function everywhere, and this function cannot satisfy this inequality, I mean, in this region, right? Because the right-hand side, the main term here will be 0, but this will not be 0. So I must have some kind of an error. Okay. Okay. In fact, one can show that if I know a priori bound on U, for example, if I know that U is a priori a polynomial of degree d, then I can show that after n, for n bigger than d square approximately, there will be no error, in fact. But if we don't have any bounds on the polynomial, that we must have this error also. Okay, and the second remark which I want to say about this statement is the coefficient 2 here, which also some people may not like it. So in fact, it should be 1, right? But what we can show that, so remark 2, we can show the theorem with is 1 plus epsilon instead of 2. But then we pay a price. The price we pay here that for the error, instead of having n to power 1/2, we have n to power 1/2 minus epsilon. So we don't know how to get the constant for epsilon equals 0. So, and the third remark which I would like to say is that after we proved the first theorem about absolute monotonicity, and while we were on the way to deduce a corollary of this form, I met Zhenya, and she told me that she had, with her student, she had a version, she exactly formulated a version which looks like this, but for L infinity norms, and so we were inspired by her formulation. So in fact, the error term, which appears in Eugenia's formulation, we had the same thing, but after we saw her formulation. And okay, so I think so. And this was about L infinity norms. Okay, so let me say how to how you see that this corollary is immediate from the theorem on absolute monotonicity. So here the proof of the corollary. Maybe I write it here.
Are you sure that you wrote what you meant, n to the power 1/2 minus epsilon? Because if epsilon is 1, then you...
Is epsilon the same in 1 plus epsilon and 1/2 minus epsilon?
Yeah, no, it's not. It's not, yeah, probably. Yeah, here it should be e to power minus n. So I don't remember, but you're right. That n to power epsilon, something like this. So it's not.
No. You need something which you need something which will give you 2.
You're specializing your statement.
No, but this 2 is not.
So you can impose
Yeah.
1 plus epsilon at the cost of.
Yeah, but okay. So maybe there is also.
Epsilon.
Is this okay? I mean.
No, because if epsilon... Oh, well,
Okay, let's see the proof.
It could be true, it's much worse.
1/2.
No, I will not. I will not prove the.
It's a different linear function, not a half minus epsilon.
Yeah.
Let's go.
You can't prove this with
Yeah.
the maximum principle with construction of a barrier. Like the way you
Well, it could be, but let me show you. It's a very easy corollary of the first theorem. Okay.
Okay, let's see what it is.
So the proof is like this. So first you prove it. So it's a sketch of the proof. The first thing. By the way, so maybe before I start the proof, let me give an example, a prototype example of an absolutely monotonic function. I forgot to tell it before, of an absolutely monotonic function, a discrete absolutely monotonic function. It's just f k of n equals n choose k. So this is absolutely monotonic as a function of n. So the first step in the proof is to prove that this inequality holds. But let me refer to the first inequality. Okay, so the inequality holds for n choose k. This is a function of n. And the second part is to show that if it holds for two functions, f and g, then it holds for the sum also. And this is also easy. I mean, it is well known that logarithmic convexity holds for sum of functions if it holds for any one of them. And for the error term, it also adds up. And the third part is just to observe that the third part is just to observe that if f and g, that for any function absolutely monotonic, the same fact that I mentioned before can be written as a sum of. I know that q of n can be written as a sum of functions which satisfy this inequality. And yeah, by our theorem, this is positive, so I can apply the second step and get also the theorem for the q function. Okay.
Okay, how do we do the first step?
Okay, so the first step, okay, in fact, for the first step,
That's where they are confused, right?
I mean, okay, it's, I mean, I'll just say what in fact, I prove a stronger inequality for each of these functions. What I prove, just one can check that n of k is in fact smaller than the maximum, of these 2 times the square root of 2 and choose k. Let me write, yeah. So square is smaller than the maximum of 4 times n choose k for n choose k, and 2 to the power minus k for 2 to the power minus square root of n for n choose k. Okay, just by direct estimate, it's not a difficult estimate. Okay, but then I estimate the maximum by the sum because I want it to be preserved under additivity. And then I get it for any function. Well, when we were trying to prove the theorem, it was clear that such an argument should work, because in Rn we know that absolute monotonicity implies logarithmic convexity.
So what you are saying for that kind for n choose k is that you are
Yeah. Okay, but now, okay, so I would like to speak about a few more questions regarding this. So,
Just before
yeah.
you want to move to something else, so may I ask you?
Yeah, yeah.
So if the grid of size of the grid goes to 0, still you won't get in the limit of Mon because theorem, right? You substitute into harmonic functions the Brownian motion.
Yes, yes.
Say it's something else.
Yeah, so this is a good question. We don't know, unfortunately, to say much about it. What is the relation between this random walk function and the more geometric growth function?
Is there a way after this to relate it to heat equation, maybe just to...
Yeah, it's the same. I mean, the same is true for the heat equation in Rn.
Yeah, but so
But
what you get in the limit, is it possible to...
In the limit you get,
without-
yeah.
Without probability, this is my question. So if you substitute into harmonic function the Brownian walk, and then you look at the first exit time, and then you average, so...
Not the first exit time, just the average over. Yeah. I mean, just you yeah. Then you get that Q is, but then there is another interesting question. What is the relation between this, how to approximate the Agmont function by and its derivatives by the Brownian motion function? So,
Which function?
so Q of t, you want to define right. Yeah. Yeah, that's what you want to define, yes? K is the heat kernel. So the same is true. This function is also absolutely monotonic. But then the question is, what is the relation between this function and its derivative to the Agmont function and its derivative? So.
But can you get from the limit, if you substitute here another parameter, can you get Agmont theorem as a limiting case of this?
Yeah, I'm not sure. I don't know how to do it. Yeah. Ken.
Do you have any example of a group for which Q of n is not absolutely monotonic?
Yeah. So this is I'll keep this part to the end of my talk. Okay. So I will remark about this. Okay. Okay. So now. there are two questions which I want to address. Yeah. It seems like a technical question first, but so sharpness of the question is about the two questions are about the sharpness of the error term. It's also a question which came from Zhenya. And the question is, can we replace the error term e to power minus square root of n q of 4n by e to power minus n to power 1/2 plus epsilon. Yeah, maybe a stronger. We have a smaller error.
And you're asking this for general absolutely monotone functions, and not necessarily this specific.
Yeah. Okay. So 1 point for general absolutely monotonic function, it's not true. So this is part of the why the question is interesting. For n choose, if you check the sharp error term for n choose k, this is the best error you can do. So the question in another formulation of the question is, can we construct a harmonic function for which the q function will look like n choose k? And this is, it turns out not to be an easy question. And so can we construct in fact, we don't know the answer until now. We only know it partially. Can we construct a harmonic function u on Z2 such that q of n looks like n choose k? But what we can cheat a little bit, like in some fields we can answer this question asymptotically. And in fact, if one can easily check, but that if you take the function u, if we allow the dimension to vary, then we can define u be just x1 times x2 times xk. And for this function, it's very easy computation because we know how to compute as q of n. I'll write again the formula. And these expressions are very easy to calculate for this function. And what you get is some constant times n choose k. So if we allow the dimension to be big, then we can create. So what this shows that in fact, so the claim is the following: that if for any positive constant, for any epsilon, and for any big n, natural n, there exists a dimension d, and there exists as little n bigger than capital N, such that and there exists a harmonic function on ZD such that q of 2n is bigger than this constant times square root of qn times q of 2n plus e to power minus n to power 1/2 plus epsilon. So if we allow the dimension to be big, then this theorem is sharp. But somehow this is cheating. So what we try to check also if the theorem is sharp with while fixing the lattice, fixing the dimension. And in fact, we discovered that it is in fact sharp also in Z2. So at least in Z2, we know that it is sharp. So this is a, so error is sharp in Z2. And in fact, so the same statement is true. I will not copy it. Just I can remove the dimension and replace it by 2. And I would like just to remark about the proof. In order to produce the proof, I need to find a way to construct many harmonic functions on the lattice. So we found some procedure to do it, but then we discovered that it was recently discovered also by Jerison, Levin. So I'm just telling you an ingredient from the proof. So an interesting construction of harmonic function by Jerison, Levin, and Scott Sheffield. And the procedure is like this. You start with a P. So I'll just describe it in R2, in Z2. So it works in any dimension, but just to be simple. So start from a harmonic polynomial. So for example, x to the fourth minus 6x squared y squared plus y to the fourth. Okay, so write it a little differently. So each time you have a power, write it with x to power k over k factorial, and then correct. And then now do the following algorithm. You replace each time you have x to power k over k factorial, you replace it by x choose k. So here you have x choose 4 minus 6 times 2 factorial, x choose 2, y choose 2, plus 4 factorial, y choose 4. It turns out that this function is harmonic on the lattice. And this algorithm works. So in this way, we produce a lot of harmonic functions on the lattice. And it turns out that the theorem becomes sharp for the family of functions. The error becomes sharp for the family of functions, just the standard basis real part of z to power d and image part of z to power k. I want to say that the reason why we succeed only in dimension 2 is that we use some kind of discrete complex analysis, which we don't know. At least it's much more difficult. It seems much more difficult to do in higher dimensions. Okay, so now I would like to answer the question of Asaf on other groups. Okay, so there are two. First, maybe a effect which looks maybe surprising at first. What happens on so non-abelian case? So first effect from the continuous world. So on S2, say the sphere in R3, U is not harmonic on the sphere, but just say on a neighborhood. Okay, I want to say just say hemisphere. Okay, the north. So U is harmonic on a spherical disk. then it turns out that also here, so this is a joint work with my former student Rachel Yovel. It turns out that also here it is true that all powers of Laplace are non-negative. Although the reason was mystery. I mean, we just proved it by brute force somehow. The reason was a mystery for us for some time until we found the simple reason. So the reason is the following: that it is true that
sorry, Dan, so what is S2 plus?
I mean, there are no harmonic functions on the sphere, so I need to take just a neighborhood of the North Pole. So Laplace. So in fact, it is true also on the sphere that if you take a harmonic function, then it cannot be written as the sum of squares of two harmonic functions, but it can be written as the sum of three harmonic functions squared. So this is just xu squared plus yu squared plus zu squared, where x, y, and z are the vector field which generate the rotations around the axis. So this formula is still true up to this constant 2. Okay, so since x, y, z commute with the Laplace, so this still is the sum of harmonic functions. And it seems that this can be, this simple argument, in fact, works. I mean, whenever you have a semi-simple Lie group, acting on some compact manifold. Compact manifold. So again, you can write the Laplace as a sum of squares of vector fields which commute with itself, with the Laplace. Okay. And now it seems much more challenging to address the nilpotent case. So and this is a work in progress. We don't know what much to tell. So first, yeah, right. So even in the Riemannian case, it's interesting. So, you mean in general? Sorry, in Riemannian manifold. Yeah. No, so it is not true. I mean, just not true. Yeah. And in fact, we know by Bochner that the second Laplace is positive. Okay, so from Bochner identities shows that if the Ricci curvature in fact is non-negative, then Laplace squared of u squared for u harmonic is non-negative. But not for the third power, not such a thing is true anymore. I mean,
so what is the geometric input? Homogeneous space? I mean, you run the groups. You're saying that it's not true for any Riemannian manifold, right?
Yeah.
You're saying that even curvature assumptions are not enough.
Yeah. Mm-hmm.
You also know that the law concavity, the law convexity, is false for general.
No, this I don't know, but yeah, this I don't know. The law convexity I don't
So
know.
there is no example on manifold for which a law convexity fails for harmonic functions.
Sorry, I'm sorry. Yes, so low convexity is true for harmonic function up to perturbations. Yes, so.
Okay,
Yeah.
but it doesn't come from this monotonicity, absolutely.
Yeah, it's much simpler. You need only second power. So in the results of Sasha, you use only local convexity. In other words, this is the same as saying monotonicity of the frequency function. You don't need that all powers are positive. Okay, so Yes, so now the nilpotent case looks like
Heisenberg group, not hyperbolic free space.
yeah, so how do you, what is a standard notation?
It's just disturbing that dash.
Yeah, I don't know what is a standard notation. I mean, maybe.
Both are
Maybe.
Three.
Yeah, so what so what we can say about the Heisenberg group, first it's not true that, so what is the Laplace? In this case, the natural, it seems that the natural operator to take, I mean, we know that we don't have like Casimir operator, right, like on the semi-simple case, but it seems that the natural operator to take is x squared plus y squared, while x and y are left invariant vector fields. And also I have a symplectic form, so I take the standard left invariant vector field we span okay, and then which are orthogonal to the center in some sense, and so a harmonic function is just a solution of this equation, and I should just say this operator is not elliptic anymore; it's just hypoelliptic, and it's not true, so it's not difficult to check that this is no longer true for. I mean, it's not always true, not always true. And of course, a general question would be: does this quadratic form? So we can consider this as a quadratic form on the space of harmonic functions. Say I evaluate it at the unit element. This is a quadratic form on a harmonic function. And then U is harmonic. So does this quadratic form retain some positivity properties? Can we discover from the properties of this quadratic form, for example, the step of nilpotency of the group? And we don't know how to answer this question, but I would like to say that we do know. So recently we found a proof of a very easy proof of Liouville theorem, also on nilpotent proof using a similar argument to the abelian case, although we don't know what to say about the full quadratic form. So maybe in the 2 minutes left I will say a word about the proof of Liouville in the nilpotent case. Okay, maybe here. So just to tell the idea of the argument is just the basic idea the following. So you start with U harmonic, and then you first show that the Q function for U, its derivative is bounded by the Q function of the derivative of U with respect to the center. So now if you take a harmonic function and you derivate it with respect to the center, it stays harmonic. And but for any harmonic function, it is true that the Q function, if f is harmonic, then its Q function is monotonic. Yeah, just because its derivative is the expectation of Laplace of f squared, but Laplace of f squared is always non-negative in any situation. So we have a Q prime is controlled from below by a positive monotonic function. So if Q dzu say at 0 is not 0, I want to show that suppose that U is not only harmonic but bounded, okay? A bounded harmonic function, I want to show that it is constant. So if this function at 0 is not 0, since it is monotonic, we get that Q prime is bounded by a constant from below, so Q grows at least linearly. Grows at least linearly. So this means that the derivative of in the direction of the center is 0. Okay, so I just finished by saying that. So we know that the derivative of U with respect, so U depends only on x and y. So it can by reducing now by going to the quotient, we get by induction on the nilpotency step that we have a bounded function which is harmonic on a smaller step nilpotent group. So it must be, we know that it must be a constant. So this is the way you prove it for bounded harmonic function, but this generalizes also for the polynomial version. So we have a simple argument for Liouville theorem, but still it seems that it's not clear how to prove yet positivity statements about the quadratic form. Okay, thank you.